Hello everyone and welcome back. My name is Mr. Koval, and in this video I'm going to be going over another example problem of gas stoichiometry. So let's get into this. So since we're doing gas stoichiometry, like any other stoichiometry, we have to get to moles. That is the key. So whatever unit you're given, you're going to convert that unit to moles. Why? So we can use the mole ratio just as it's shown here. So we want to get to the moles so that way we can use our mole ratio to convert from moles of one substance to moles of a different substance. And so that's why we need to get to moles. Once you get the moles and you convert from moles of one substance to the other substance, then from there you're going to convert to whatever unit that they want you to find. So let's go ahead and look at our problem and see what we need to do. So here there's two parts. Part one, or part A, what minimum volume of oxygen at STP is necessary to convert 125 megagrams, that's not magnesium, it's megagrams, of carbon to carbon monoxide. And they're giving us the equation here. So what minimum volume? So we need to find the volume of oxygen at STP. What are we going to start with? They want to convert from 125 megagrams of carbon. Okay, so we're starting with megagrams of carbon. We want to convert that to CO. In the process, we need to know how much oxygen is needed to do that. So we need to convert from the amount of carbon to an amount of oxygen needed for the carbon to react completely to form a certain minimum volume or a certain amount of carbon dioxide. Okay, so uh, we need to start with the 125. So we're going to start with 125 megagrams. 125 megagrams of carbon over 1. And so again, we're at this part here. So we're in grams, a unit of mass. So we're on this part of our highway here, our road map. And so we need to get to moles. So in order to get to moles, we're going to need to get to grams, and then we can use the molar mass to convert to moles. So let's go ahead and do that. So megagrams, we need to know what mega means. Mega means 1 million or 10 to the 6. So 1 megagram is equal to 10 to the 6 grams. So we're going to multiply by the conversion factor of 1 megagram on the bottom of carbon and 10 to the 6 grams of carbon on the top. So megagrams cancels out. Now we have grams. Now we can use the molar mass to convert to moles. So what's the molar mass of carbon? We look that up on our periodic table, and we find that 12.011 grams of carbon is equal to 1 mole of carbon. So now grams of carbon cancel out. Okay, so now we have moles of carbon. Now we're here on our roadmap, and now we can use the mole ratio from the balanced equation to convert from moles of carbon to moles of the oxygen. So it's a 2-to-1 ratio. So we're looking at the coefficients, 2 here, 1 here. So 2 moles of carbon for every 1 mole of oxygen. So we write that down as our conversion factor. So I have moles of carbon on the top. So I'm going to put 2 moles of carbon on the bottom and 1 mole of oxygen on top. So moles of carbon cancel out. Now I'm at moles of my second substance. So now I'm here. What are they asking for? They want to know the minimum volume of oxygen. So let's go ahead and do that. Now, since we have moles of oxygen, we want gas. We want volume of gas. So we're going to have to go this way. So we're going to have to use the PV equals nRT, the ideal gas law equation. We're going to convert that to liters. And then we're going to need to convert probably to, well, probably liters is going to be fine since this is a huge amount of gas. We're probably going to want to use a larger volume. So we're going to stop at liters since they don't tell us what volume. Liters is good enough. So now I'm going to use the R constant for the ideal gas law. So the ideal gas law constant, that's going to be, we're going to use the 0.028058 number because that's liter atmospheres per per mole Kelvin, and they're giving us STP. Now we will come to that in a moment, but you need to know what STP is. So let's just set up our conversion. So since I have moles on the top here, I want moles on the bottom for my ideal gas law constant. So we're going to put 0.08205.8, and that's going to be liter atmospheres on top, and it's going to be Kelvin mole on the bottom. So here, moles of oxygen are going to cancel out with moles. Okay. And then, oh, I'm sorry, not oxygen though. Sorry, don't want to cancel out oxygen since we're talking about oxygen. We want oxygen, but moles is going to cancel out. So moles. And then what about the Kelvin and atmospheres? So that's where the STP comes in. So we need to remember that STP stands for standard temperature and pressure. Well, what is standard temperature and what is standard pressure? Standard temperature is 0 degrees Celsius, or in Kelvin, that would be 273.15 Kelvin. The standard pressure is going to be 1 atmosphere. So all we need to do is use that atmosphere and that temperature as conversions. So since Kelvin, excuse me, and so we're going to use that as a conversion. So here, and so since we have Kelvin on the top, on the bottom, we're going to put Kelvin on top. We're going to put the temperature on top. So the temperature is at, again, 0 degrees Celsius or 273.15 Kelvin on the top. So Kelvins were canceled out. And then on the bottoms, since we have atmosphere on top here, we're going to put the pressure in atmospheres on the bottom. Again, standard pressure is 1 atmosphere. So we're going to put 1 atmosphere here. So then the atmospheres cancel out, leaving us with liters. So we are now done. All we need to do is go ahead and calculate this out. So this is going to be, we're going to multiply across the top and divide by everything on the bottom, and we'll get our answer. And when we do, it is 1.166 times 10 to the 8th liters of oxygen. So that is the amount of oxygen we need to react completely with 125 megagrams of carbon. So let's go back to sig figs here. So for those of you interested in the sig figs, remember what we need to do is limit this to the number of sig figs required. So the rule is when you're multiplying and dividing, that the number of sig figs in your answer should be the same as the number of sig figs in the measurement with the least number of sig figs. So let's see which one of these has the least number of sig figs. So this has 3 sig figs. This is exact, so we can ignore this. So metric mass to metric mass is exact. Here we have 5 sig figs in the molar mass. This mole ratio 1 to 2 is exact, so we can ignore that. This has 5 sig figs in it, and this has 5 sig figs, or at least actually it has 3, because when we added it to the standard temperature in 0 degrees Celsius, that has zero decimal places, so we can't extend past the ones place. So that has 3 sig figs. So the least number of sig figs is 3. So we would have to limit this to 3. So we would cut off 1, 2, and 3. Cut off there. That's a 6. So we got to round that to a 7. So that's going to be 1.17 times 10 to the 8 liters of oxygen. And so that's the answer to part A. What about part B? What is the maximum volume of CO at 1.05 atmospheres and 35 degrees Celsius that could form from the conversion of this many liters of oxygen at this atmosphere and this temperature? Okay, so we're going from gas to gas. We're going from a given amount of oxygen. So we're given this many liters of oxygen at this pressure and temperature, and we're going to have to find the maximum volume of CO at this pressure and temperature. So again, we're going to start with the amount of oxygen we're given. And so here we're going to have 8 point, here, let me move this over, just give myself a little bit more room. We're going to have 8.74 times 10 to the 5th liters of oxygen. We're going to put that over 1. And where are we? So we got liters of oxygen. So here we got a volume unit of a gas. And so we're going to need to convert. Now we're given liters, so we're here on our side road. So we want to get on the main highway, and that's going to bring us to moles. Remember, you always want to get to moles first. So here we got liters. We're going to use PV equals nRT. So we're going to use the R here to use it as a conversion factor, and then use the volume, or use the the volume, and or no, not the pressure and the temperature we're given to convert to moles. So let's go ahead and do this. So here we got liters on the top, so we want liters on the bottom for R. So remember, the R value we're going to use is going to be 0.082058 liter atmospheres on top divided by mole Kelvin. So we're going to have to flip that to get liters on the bottom. So the 0.082058 is going to be on the bottom with the liter atmospheres. And then on the top, we're going to have Kelvin mole. So then the liters cancel out. And then we want to cancel out Kelvin and atmosphere. So that's where the atmosphere is here and the temperature here. We're going to have to convert the 27 degrees Celsius into Kelvin. So we can do that up here. So 27 degrees Celsius plus 273.15. That's going to give us, let's see here, that's 280, 300. So that's going to be 300.15 Kelvin. And so we're going to underline the 0 there, because remember, we have 0 decimal places here. So we have the ones place. So remember, when you're adding and subtracting, the number of digits you keep is going to be related to the least number of decimal places. So here, this has the last digit is in the 100th place, and the last digit here is in the ones place. So this is the last digit. So this is the one. This is the least precise measure. So we're going to go with the least precision. So we're going to stop at the ones place here. So we stop there. And so that is going to be the number. We're going to use this number for further calculation. But as far as sig figs go, we got to remember that the 0 here is where we stop. Okay, so Now that I have the temperature, I have Kelvin on the top, so I'm going to put Kelvin on the bottom. So the temperature 300.15 Kelvin. I'm going to put a line under the 0 to indicate that that is my last sig fig. And then, excuse me, next is atmospheres. So I want to put, where's the atmospheres? Here it is, 0.994 atmospheres on top. So 0.994 atmospheres. And so that's going to cancel out with atmospheres here. And so Kelvin cancels out here. And so moles is what's left. So I have moles of oxygen now. Now that I have moles of oxygen, I am here. So now I can use the mole ratio from the equation to convert from moles to moles. So let's go ahead and do that. So what are the moles we're looking for? We're looking for the moles between oxygen and CO2 or CO. So we got oxygen and CO, so it's 1 to 2. So since I have moles of oxygen on top, I'm going to put moles, moles of oxygen on the bottom. So I have 1 mole of oxygen, so that's going to go on the bottom. 1 mole of oxygen and 2 moles of CO on the top, so 2 moles CO. So moles of oxygen cancel out with moles of oxygen. And now I have moles of carbon monoxide, CO. So now I'm here. And so what are they asking for? They're asking for the maximum volume. So we need to get to liters again. So we're going to have to convert to liters of this gas. So we're going to have to go back to using the R and then the R value, and then canceling out with the new set of atmosphere and temperature. So let's go ahead and do the R again. This time I have moles on the top. I want to convert, I want to cancel out moles by putting it on the bottom. So this time it's going to be 0.082058 on the top with liter atmospheres. And then I'm going to put Kelvin mole on the bottom. So moles are going to cancel out. And so now I want to cancel out Kelvin and atmosphere to leave behind liters. So this is where I'm going to use the liter. I'm going to use the Kelvin temperature and the atmospheres and to cancel that out. So I'm going to continue down here. So I have atmospheres on the top up here. So for my next conversion, or my next conversion, I'm going to have atmospheres on the bottom. So how many atmospheres? 1.05 atmospheres. So 1.05 atmospheres on the bottom. And I need to convert the temperature again. So here I have 35. So I'm going to take 35 degrees Celsius at 273.15, and that's going to be, let's see, 308. So 308.15 Kelvin. Again, the last digit here in the ones place is the final digit of significance. And so I'm going to put that on top here. So that's going to be 308.15. And again, I'm going to put a line under the 8 to remind myself that there's only 3 sig figs there. And so the atmospheres on top cancel out with atmospheres on the bottom. This is Kelvin. And the Kelvin on top here is canceling out with the Kelvin on the bottom there. So the only thing left is going to be liters. So that is the volume unit, and they're asking for the maximum volume, so we'll stop at liters. And so now all I need to do is calculate by multiplying across the top on everything and then divide by everything on the bottom. When we do that, we get 1.6988. 1.6988 times 10 to the 6 liters of, what am I talking about? CO. CO. So that's the volume needed, the volume of CO needed, or that's going to be produced, that's going to be produced from this amount of oxygen gas. Now, with regard to sig figs, for those of you who are interested in sig figs, I need to limit this to the proper number of sig figs. Remember, the rule for multiplication and division is that your answer should have the same number of sig figs as the measure with the least number. So let's look at our measurements. So this one has 3 sig figs. This one has 5. This one has 3. This one has 3. This is exact. This mole ratio exact. So we are going to ignore that. That's 5. And then here we have 3. So the least number is 3. So that means our answer should only have 3 sig figs. So we're going to count 1, 2, 3. So the 9 is last. Cut everything else off. And so this is an 8. So we're going to have to round that 9 to 10, which means that the 6 gets rounded to a 7. So 1.70 times 10 to the 6 liters of carbon monoxide. And so that, ladies and gentlemen, is the answer. I hope you enjoyed this video. If you learned anything from this video, if you enjoyed this video, then please, by all means, like the video, share the video, hit that like button down there. Also, subscribe to my channel, hit that notification bell. And when you do, make sure you click all so you'll be notified by all the videos I put out. Finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a question or problem you want me to go over to help you with, or if you have a topic you want me to cover, I would love to do that for you. Thanks for joining me and have a great day.